We first look at the items that make up a microcontroller. This is called system hardware as opposed to the programs which are referred to as the software. A computer is made up of 4 basic functional units: the central processing unit or CPU, the memory, input and output I/O. The central processing unit does the actual computing and is composed of 2 subparts, the arithmetic logic unit and the control sections. The arithmetic logic unit, or ALU, performs the actual numerical and logical calculations such as addition, subtraction, and so on. The control section of the CPU manages the data flow such as reading and executing the program instructions. If data require calculations, the control section hands it over to the ALU for processing. In a microprocessor-based computer, the microprocessor is the CPU. Digital data is in the form of bits, where each bit has the value of either 1 or 0. Digital circuits usually use 5 volts DC to represent logic 1 and 0 volts DC to represent logic 0. 8 bits together is called a byte, and a microprocessor handles digital data in words, where a word may be 8, 16, or 32 bits wide depending on the width of the bus. For example, an 8-bit microprocessor has an 8-bit byte-sized word with a maximum decimal value of 255. The rightmost bit in a binary number has the least value and is called the least significant bit, or LSB. The leftmost bit represents the highest value and is called the most significant bit, or MSB. The conversion between binary and decimal can be performed directly with most scientific calculators or manually using the technique as shown. To express values larger than 255, 2 or more words are put together. In this course, we will assume 8-bit microprocessors are used, unless otherwise stated. If you require more info on binary numbering, try watching the video Binary and Decimal Conversion, which will be in the Additional Resources section of this course on Blackboard. The memory section of the computer is a place where digital data in binary form, in ones and zeros, are stored. Memory consists of cells organized in 8-bit groups. Each byte is given a unique numeric address which represents its location, just as a street address represents the location of a house. Data are written into memory and read out of memory based solely on their address. In a particular memory circuit, the addresses might start at 1000 and run consecutively to 2000. This represents a section of memory. Note that the first byte of data has a decimal value of 2, or 00000010, and an address of 1000. Computers usually have 2 kinds of addressable memory. The first is random access memory, or RAM, which allows the computer to read and write data at any of its addresses. It is called read-write memory, or RWM. All data in this type of memory are lost when the power is turned off and is called volatile memory. An exception is designs where the RAM is kept alive with a small battery. The second type of memory is read-only memory, or ROM, which is similar to RAM except that new data cannot be written in. All data in ROM are loaded at the factory and cannot be changed by the computer. This memory does not lose its data when power is turned off and is called non-volatile memory. Most microprocessor systems have both RAM and ROM. RAM is used for temporary program storage and as a temporary scratchpad memory for the CPU. ROM is used to store programs and data that need to be always available. Actually, many computers use an EEPROM, which stands for Erasable Programmable Read-Only Memory, or an EEPROM, Electrically Erasable Programmable ROM, instead of a ROM for long-term memory. EEPROMs can be erased by a strong UV light and reprogrammed, and EEPROMs can be erased and reprogrammed electrically, which allows engineers to change control programs to suit their applications. Disk drives also store digital data, but in a form that must be processed before they are accessible to the microprocessor. The input-output, or I/O section of the computer allows it to interface with the outside world. The input section is the conduit through which new programs and data are entered into the computer, and the output section allows the computer to communicate its results. An I/O interface is called a port. An input port is a circuit that connects the input device to the computer. Examples of input devices are keyboards, sensors, and switches. An output port is a circuit that connects the computer to output devices. Examples of output devices are indicator lamps, actuators, and monitors. Input and outputs are discussed in more detail in the next section. We see that the blocks are connected by 3 lines labeled address bus, data bus, and control bus. The address bus is a group of wires that carries the address in binary form from the CPU to the memory and I/O circuits. The need for memory to receive addresses has already been discussed, but you may wonder why the I/O ports need addresses. It turns out that all I/O ports are assigned addresses and are treated essentially like memory locations by the CPU. The CPU outputs data to the outside world by sending them to a port address. When the circuitry of the designated output port detects its assigned addresses on the address bus, it opens and allows data to pass from the data bus to whatever is connected to the port. There are 2 ways that I/O addressing is done. Some microprocessors use what is called memory-mapped input-output, where the I/O address is treated just like another memory. Other microprocessors treat I/O addresses completely separate from memory addresses. The data bus is a group of 8 wires that carries the actual numerical data from place to place within the computer. Remember, we are dealing with 8-bit processors. If we used a 16-bit processor, the data bus would have 16 wires. Data flow in both directions on the data bus. For example, input data enter through the input port and proceed through the data bus to the CPU. If the CPU needs to store these data, it will send the data through the data bus to memory. Data to be outputted is sent by the CPU through the data bus to the output port. If the data bus connects to all blocks, how do the data know which block to go to? The answer is the address system. For example, when the CPU sends data to memory, it does it in 2 steps. First, it puts the destination memory on the address bus. Second, it puts the data on the data bus. When the designated memory detects its own address, it wakes up and takes the data from the data bus. The other blocks connected to the buses will ignore the whole sequence because they were not addressed. A good analogy here is the phone system, where the phone number is analogous to the memory address. Even though thousands of phones may be connected to the system, when you dial a number, only the designated phone rings. The beauty of the bus system is that it is expandable. Memory and addressable I/O units can be added to the system by simply connecting them to the buses. The control bus consists of timing and event-controlled signals from the CPU. These signals are used to control the data flow on the data bus. For example, one of the control signals is the read-write or R/W line. This signal informs the memory if the CPU wishes to read existing data out of memory or write new data into memory. Non-memory mapped machines have a memory I/O control line. This signal informs the system if the current data exchange involves memory or an I/O port. In general, the control bus is not as standardized as are the address and data buses.